A discussion of string scattering. Today's lecture is going to be now devoted once again to tree level amplitudes, but this time to the open string. Okay, and now I can't even remember, since it's been so long since we started, how much we discussed the open string in the first course.
Too much.
Huh?
I think we exclusively discussed that.
Closed string. Very good. So let's do it from scratch.
And maybe some of the labels, giving light on quantization,
But yeah,
mostly
minorly.
Yeah.
Okay, so let's start with the bosonic string. You remember that the worldsheet action was 1 by 4 pi alpha prime del alpha x square root m. Okay. When discussing the open string, as we'll do all the usual Polyakov tricks. So once again we are back into the standard form action, 4 pi alpha prime d2 sigma del mu x or del alpha x, now in flat space of the worldsheet. We move to the conformal frame, and we've used the fact that the action is independent of phi. Once again we'll be in 26 dimensions, and all that will be the same. I think the local physics will be the same. What we're now going to try to do is to investigate the possibility of putting boundaries on the worldsheet of the string. Okay, so let's see. Suppose we want to put a boundary on the worldsheet of the string. In order to have a classically well-posed system, we need to put boundary conditions. What kind of boundary conditions do we need? Well, in order to understand that, it's useful to imagine that we are working in coordinates in which this is tau and this is sigma. We will always choose sigma to vary from 0 to pi, unlike 0 to 2 pi for the open string, and you will see why. You will see why this is a convenient choice. Okay, so now, but at the moment I'm going to ask the following question. Near x equals 0, for instance, okay, near x equals 0, for instance, what kind of boundary conditions do we have to put on x in order to get a well-posed classical problem? Okay, so what we want is, let's say that what we want is nothing, is to get is to have boundary conditions so that the equations of motion will follow from an action principle. Usually a good thing to demand. Okay, so the equation of motion as before is del squared x is equal to 0, but how did we get that equation of motion from varying this action? Well, we varied this, right? So we made this delta x. There were two such terms, but let's take any one of them. And then what we did was to take delta x times and then integrate it by parts. But there was a total derivative. There was a total derivative that, so it was del alpha x, delta x, plus or minus delta x times del squared x. Right? 1 by 2 pi alpha prime, because there are two such terms. When we varied, this is what we found, and then we set the coefficient of this delta x term to 0. That gave us del squared x equals 0. For the closed string, that was all that there was to do, because this total derivative integrated to 0. But now with the open string, it's not all there is to do, because of the boundary. So this quantity here evaluates to this object evaluated at the boundary. So let us take this particular configuration. The boundary, let's say, is that sigma is equal to 0, or sigma equals pi, it doesn't matter. Okay, so what derivative is active for the total derivative? This is the sigma derivative, right? Alpha here, that matters. So that's the sigma derivative. So what we get is that the boundary term is del sigma x, delta x, integrated over the boundary. Right? Now, if we want to demand that this does not contribute to the equation of motion, that the equation of motion remain delta squared x equals 0, not delta squared x equal to some delta function sourced at the boundary, this is usually a good thing to do. Okay? If we want to demand that, then we have two options. Then it must be that everywhere del sigma x times delta x equals 0. Okay, so there are two reasonable options. So product of two terms equal to 0. So either this term is 0 or that term is 0. Okay, this term is 0 would mean that the boundary of the string is fixed to lie at a particular x. Okay, now that may or may not be something interesting, but it's not of interest to us at this stage because that would break translational invariance in spacetime. We're trying to, at the moment, build a translationally invariant string. In fact, that's the boundary condition we will use when we discuss d-branes, which in fact do break translational invariance because they object in spacetime. But that's at a later part of the course. Right now we just want to understand open strings moving around all of spacetime. Okay, so because of translational invariance, also rotational invariance, meaning if you choose a particular point in x mu, it preserves neither translations nor rotations. Okay, so from all the symmetries, the Lorentz symmetries of our problem that we want to preserve, we won't choose this boundary condition. We will instead choose this boundary condition. Okay, so we have the boundary condition del sigma x mu is equal to 0. This is the boundary condition we're going to impose at the boundary of our string. Okay, now more geometrically speaking, what that is the condition that the normal derivative of x at the boundary vanishes. That of course is what you got from here, right? Because Stokes' law gives you normal derivative with respect to the boundary. Okay, so more geometrically speaking, we're imposing the condition that the normal derivative of x at the boundary vanishes. Okay, great. So now, as before, okay, good. So and this is going to be imposed on every condition, every mu coordinate. 0 to 25. Clear? Excellent. Now, there is an interesting effective way to deal with this boundary condition, as I will now try to explain. Okay, firstly, if we did a mode expansion, since we have this normal derivative vanishing both here and here, then it's clear that a mode expansion will be, I'm not touching the 0 modes, so nothing really changes there.
Because the cost will be there instead of that.
Exactly, exactly. Will be in terms of cos n pi, cos n sigma, cos n sigma. Right? The earlier expansion, that I'm not looking at time dependence yet, just expanding configurations. The earlier expansion, which was in terms of e to the pi n sigma, is now forced to be in terms of cos n sigma, because of the boundary condition that at 0, the sigma derivative of the thing vanish, and at pi, the sigma derivative of this vanish. Clearly, this works for cos n. Clearly, it's the only thing for which it works. Okay. Now let's expand out this cos n. So this is equal to a n into e to the power I n sigma plus e to the power minus I n sigma. Then by 2. Okay. Okay. Now, how will time dependence go? Well, we know the time dependence, all solutions of del square x equal to 0 are either analytic or anti-analytic. Okay, so the time dependence is going to be, this guy is going to be replaced by, so there are various options, right? This guy could be replaced by plus minus t, and this guy could be replaced by plus minus t. Okay, but we want this, we want our boundary condition. So let's first put this. So we want sigma plus minus t tau and sigma plus epsilon tau. This plus minus and that epsilon need not at this point be the same. Right? The most general solution to the equations of motion will look like this. Okay, but now let's see. What we want is that this quantity here had, were this relative phase to become different,
It would not hold for all time.
yeah, it would not remain a cos. Right, it would be some, the relative angle inside the cos would change. So the boundary condition would be violated. Okay, so that tells you that if you put a plus here,
Yeah, there has to be a plus.
has to be a minus.
Minus, sorry.
Yes,
So there's minus outside.
because there's a minus outside. Okay, and then of course you could have the reverse. You could have minus there and plus there. But the important point was that if you had this as one object, this guy is the other. So what you're seeing is that what's happening by this boundary condition is that if you know the analytic part of the field, you also know the anti-analytic part of the field. Left movers and right movers are not independent anymore. Do you see this? Right? If I just gave you this, then you could reproduce this part. The same information, the an, that's the coefficient here, is also the coefficient for this object. Okay? So this is the most important thing about the open string. That is that whereas for the closed string, we would have had one an here and one an tilde here. For the open string, we have the same an behind both the left moving and the, we are halving of the amount of data. Notice halving of the amount of data with the same periodicity as for the closed string. Because in the closed string we expanded e to the power I n sigma. That's why we chose this to be pi. The cosine is a cosine with the same frequencies as you would have had for periodic boundary conditions. Because half of the mode of the cosine fits into this interval. Is this clear? Now, I want to say this a little more geometrically. Is this clear? The important thing is here is that if you have the analytic part, you also know the anti-analytic part. There's no additional data. So it's half as much data as for the closed string. Okay, it's a special example of the Taylor expansion of solutions of the closed string with some particular restriction. Basically, A is equal to A bar. It's not clear from this. Well, suppose you took the closed string and you expanded, you would have expanded as e to the power I n sigma. That's the same expansion. So that's why, had I chosen the strip to have been 2 pi, then you would have got an effective closed string with length 4 pi. You know what's going on here? What's going on is that the first mode, for instance, is this guy. This over pi completes to this over 2 pi. Is it clear? Okay. Okay, very good. So now I want to say this last thing a little more, in a way that will be more useful for us. And for that I'm going to do the conformal map. So let us remember how we worked previously. Previously what we did was we had omega is equal to sigma plus I tau. Let me work with, if I put a minus instead of a plus, we'll run into problems with Polchinski. So let's follow his conventions. Fine, Polchinski, great book to read, but hard book to look up formulas somehow.
Chapter 2.
Right, right. I'm looking at chapter 2.
I mean the first 2 pages.
First 2 pages.
Yeah.
No, but this conformal map is there. I need.
Conformal map is probably.
Yeah. Give me. Okay, but let's just 1 second. State operator map. Okay. So let's say W is equal to sigma plus I tau. That's great. He calls it sigma 1 plus I sigma 2. And then Z is equal to e to the power minus IW. Okay. This is chosen so that
The past infinite time is at the origin.
at the origin, exactly. So notice that if we take the modulus of Z, so mod Z is equal to e to the power minus I times I tau. So that's equal to e to the power tau. So tau equals minus infinity, goes to the origin as we wanted. It has the disadvantage of having sigma increase go that way, anti-clockwise, because of the e to the power minus I sigma. But okay, we'll just follow Polchinski. We could have fooled around with that to make it better, but we'll follow what it is. Okay, so what we're going to do is to do this same transformation. So this W was our strip coordinate. Okay, and we're going to do the same transformation. Earlier, what we did was we took the cylinder and that was mapped to the plane. Now we have to understand what we're going to get. Okay, so clearly we're going to map to some part of the plane, but which part? For that we have to know where the boundaries map. So let us sit first at sigma equals 0. Okay, at sigma equals 0, Z,
Half plane or lower half.
exactly, Z is equal to e to the power minus I, but sigma is 0, so that's I tau. So that's e to the power tau. This is sigma equals 0. On the other hand, sigma equals pi, we have minus e to the power tau, because there's an extra factor of e to the power pi. Clear? As tau varies over all values, this guy ranges from 0 to infinity. Okay? And on the other hand, as tau varies over all values, this guy ranges from 0 to minus infinity, so the boundaries are clearly here. So one of the boundaries maps here, and the other boundary maps here. Okay. Finally, if our sigma ranges from, let's say, 0 to pi, if our sigma ranges from 0 to pi, yeah, we get e to the power tau times minus I sigma. Yeah, this is an irritating thing. Does he really want to be in the lower? Yeah, it's irritating, right? I'll just check what he does. He has Z is equal to minus. In order to deal with this. Okay. So the net result is minus of anything here is up here. So the net result is that we have the upper half plane. Okay. Great. So where we are is this region, the upper half plane. Now, we had a boundary condition. The boundary condition was that the normal derivative to this surface here of x was 0. Now notice here also we had a normal derivative. surface of x was 0. Now suppose it had mapped to some region here, then this point would have been a very singular point. Because as you approached it, the normal derivative this way would have been 0, here this way would have been 0, it would have been sort of crazy. But because this is just straight, the boundary condition here just carries over to the boundary condition here. In fact, there's nothing special about this point. Okay? This we saw before. When we were looking at the cylinder, the origin from the point of view of the cylinder was a very strange place. It was at infinity or minus infinity. But from the point of view of the plane, it was just any old point. This is the open string version of that statement. Okay? So that is something very nice. What this has done, this map has done, is it's taken two boundaries and make it one boundary. The two boundaries just sort of smoothly join onto each other with no memory that they had originally been two boundaries. Now, of course, had we had a state on the strip, the same state operator map kind of issues would work. That would lead to some insertion of this operator here. As before.
Anywhere on the line.
No, not anywhere on the line. Had we had a state, that would have been all the way down.
Yeah, asymptotic.
Yeah. So, of course, then anywhere on the line by translational merits. Meaning we could have chosen any point to be a boundary.
Yes.
That's what you were saying. But had we chosen this transformation, then the state would lie here. Okay? So, that's what that's saying is that if you take a string that's not wiggling when you go down to infinity, and you do this map, it just becomes smooth. But if it's wiggling, that wiggle gives you something not smooth here, which is captured by an operator insertion. Okay? It was the same with the cylinder. Took just a straight cylinder, you did the transformation, infinity was some smooth point. But if it was wiggling, that wiggle was captured by the operator insertion. All the same things, and we're not going to go over, say all the words again in detail, because it's just the same thing as for the closed string. Just reminding you of it. Okay, excellent. So now we've got this nice thing with one boundary. Lovely. Now we're going to try to write down what the boundary conditions are. Well, the boundary conditions, of course, are the normal derivative is equal to 0. So if we call this coordinate y and this coordinate x for a moment, of course, we have z is equal to x plus iy, or sigma 1 plus I sigma 2, whatever. Okay? Then our boundary condition at y equals 0 is that del y of x is equal to 0. But what is del y in terms of z and z bar? Because now we're sophisticated people, right? We're not like we were at the beginning of the course. We know z and z bar are the good coordinates. So that's del z x del z by del y plus del z bar x del z bar by del y, right, by the chain rule. Okay, but this quantity here is I, because z is equal to x plus iy, and this quantity is minus I. So we get I into del z x minus del z bar x is equal to 0, which is the condition that del z x is equal to del z bar x. This makes a lot of sense if you think about it. You see, once you come down to the boundary of the string, the normal derivative vanishes, and therefore the derivative is purely in the tangential direction. But at the bound, at z equals at the real axis, z and z bar are distinguished only in going off the real axis. Along the real axis, they're the same. Okay? So, if del z bar is equal to del z, that tells you that they're both varying only in the tangential direction. Right? Because both of them, up to some factor of 2 maybe, are del sigma, or del x. If the variation is purely along the boundary. So this condition is same as saying the variation is purely along the boundary. We're giving intuition for this algebra. The algebra, of course, establishes it without confusion. Okay? Wonderful. Now that we have this, we can keep going. See, since del z of x is equal to del z bar of x, we can do this very beautiful thing, which is the following. Our string was only defined on the upper half plane. So let's say that the string was z of x plus z tilde of z bar. Right? Because it's some analytic solution plus some anti-analytic solution. Up here. Now, these are not independent of each other because they have to meet this condition. Okay? These are not independent of each other because they have to meet this condition. And that condition precisely does the following thing. Suppose I define z prime is equal to z bar star. Star is complex conjugate. Now, this is a bit confusing, so let me say it very clearly. Z was equal to x plus iy with y greater than 0. No, I don't want the star, sorry. Sorry, yes, I want z prime is equal to z bar. Sorry. Okay? So z bar is equal to x minus iy with y greater than 0. But now what I'm going to do is define a new coordinate. Okay? So z prime is x prime plus iy prime, which by definition is equal to x minus iy. So these coordinates are simply that x prime is equal to x, but y prime is equal to minus y. Exactly. So while z bar is the bar of a quantity that lives in the upper half plane, if we identify z bar with some new z, that of course lives in the lower half plane. I'm just saying, well, all I'm saying, I've said it very wordily, all I'm saying is that if z lives in the upper half plane, z bar lives in the lower half plane. And whatever that z bar is, we're going to call z prime. It lives in the lower half plane. Obvious thing. Okay. Now I define the following thing. I define an analytic function defined on the whole complex plane. And it's defined like this. It's equal to x of z in the upper half plane and is equal to x bar of z equals z bar. Let's just call it x bar of z. Do I call it bar? X tilde. X tilde of z in the LH. Do you understand what I mean? This is a function of some argument. That argument was well defined as a complex number in the lower half plane because it's the bar of an argument which was well defined in the upper half plane. Now, that argument I will just continue to call z. Okay? You might think I'm doing some trickery here, and you have to it takes a couple of minutes to get your mind around it. Okay, and maybe I could use some more notation.
No,
yes.
probably you don't have to use cos c. You can just use one exponential and just define it everywhere.
Yes, exactly.
So you are equivalently mapping the upper half plane to the full complex plane by some conformal transformation.
Not a conformal transformation. I'm using the analytic part. Will continue to live in the upper half plane, but the anti-analytic part is mapped to an analytic function
On the full complex.
On the lower half plane. So the whole, okay. But you know, we still have to do something. At the moment, this is just a definition. For this definition to make sense, this function z should be
continuity.
Should be smooth at the real axis. In particular, we have to know whether this function z obeys this boundary condition without some discontinuity. Okay, so this
Function have to match and the
derivatives have to match, and then analyticity will ensure everything else.
How will it ensure the function matches at that point?
How will it ensure the
Derivative will match.
Ha.
Because that's what we are important.
How will it ensure the function matches at that point? It's, you know, it's because this the only thing that is not in the derivative is the zero mode. And there's only one zero mode, there aren't two zero modes.
Yeah.
So there wasn't even a question about the zero mode. Okay, so you know, everything is expanded as z plus z bar except the zero mode, which is just one guy. So take the zero mode out. That's on its own trip. We're looking at everything else. Okay, so everything is in the derivative. Okay. Now let's go back. Let's go back here. So what we have to do is to ensure that this object here is smooth, but we know that del z is del z bar on the real axis, and therefore this is smooth. By which I mean, if I take this function x and I restrict it to the real axis from below, and I restrict it to the real axis from above, these should match. That's the condition. Okay? But on the real axis, del z and del z bar both del sigma. Right? So on the real axis, you see, below it was defined by x tilde. Above it was defined by x. The condition that it matches is simply the condition that del sigma of x tilde is del sigma of del x, del sigma of x is del sigma of x tilde. Because this guy becomes del sigma of x, and this guy becomes del sigma of x tilde. But we know that those are true. Okay, there are many ways of saying it. But it's clear that this boundary condition is compatible with this identification. And then after that, it's easy to convince yourself that analyticity makes sure that this is a completely smooth function. For instance, if you do a mode expansion, this is the z version of that mode expansion thing I was giving you. That mode expansion thing would be to redefine sigma to pi minus sigma in the other guy of the cos. You know, cos has an e to the power n sigma, then there's an e to the power minus I n sigma. And in the other chap in the cos, you define a 2 pi minus sigma. We won't do this, but that completes the circle. These are basically the same thing.
Reflecting waves from that are just going down.
Exactly. Instead of looking at the reflecting wave going back like this, you're inverting it so the reflecting wave goes like this. That's the z bar goes to z. Okay? I know from my own experience that it takes like 5 minutes to get your head around this to make sure nobody is selling you a used car. So take the time. I mean, you get the chance. But it's very simple stuff. It's just some trivial kinematics.
Can I say that if I start with a closed string,
Yeah.
only look at the analytic part of the closed string and do some sort of identification on this?
Yes.
That is equal to open string.
Yeah. That's only one small difference, and that is that the relative normalization between the zero mode and the oscillator part changes. Because the zero mode continues always to be just 1, whereas the oscillator part has also become 1 now. So because of that, there is a small difference in the mass shell condition of the open string. In fact, let's work that out. Let's work that out. We had, if you remember, for the closed string, we had m squared is equal to 4 by alpha prime, 4 by alpha prime into n minus 1, which is also equal to 4 by alpha prime into n bar minus 1, by level matching n and n bar were the same. Okay? Let's remember how we got that for the open string, and then we'll get the same thing for the closed, for the closed string, and then we get the analog for the open string. So how did we get this for the closed string? Well, what we did was to put the condition that L0 was 0. That's where this came from. We got this from L0 is equal to L0 bar is equal to 0. Okay, all Hamiltonian is equal to 0. Okay, and let us remember what the Hamiltonian was. So first let's work out the 0 mode part of the Hamiltonian. We had 1 by 4 pi alpha prime, and then x dot square, because 0 mode has no x prime. Okay, so then we had a 1 by 2 alpha prime x dot square. Okay, and so the 0 mode part of the Hamiltonian was alpha prime by 2 p square. That then, with some sign, was equated to the oscillator Hamiltonian. Okay, the oscillator Hamiltonian was L0 plus L0 bar. The oscillator Hamiltonian was L0 plus L0 bar, and that was the thing which, in the absence of zero mode shifts, would have given you the level. Okay, so this was basically n plus n bar. Okay, now the zero mode shifts shifted both of these by 1, and that doesn't seem to be giving us the right answer. Just where did I get that wrong? Just a minute. Just maybe I got the Hamiltonian wrong. So a factor of 4, right? Yes. Sorry. Two by alpha. Oh, they do have. They have 2 by alpha prime. Did I remember that wrong? Sorry, Pulchinski has 2 by alpha prime n plus n tilde minus normal ordering. Let me. Sorry, I'm just gonna. We'll figure out this one. This was correct. n plus n tilde minus normal ordering, right? Minus some normal ordering constant. The point was that this normal ordering constant was minus 2, right? Sorry. Yeah, n plus n tilde minus 2, right? Sorry, just 1. Yeah, n plus n tilde minus 2. So that was equal to p squared was equal to 2 by alpha prime into so yeah, it was right. Because now we can use n is equal to n tilde. So 4 by alpha prime n minus 1. Or n tilde minus 1. Okay. Yeah. So the formula we remembered was right. Okay. Excellent. Now, what is the point? The point here is that you saw that the open string had the same spectrum of oscillators as the closed string, but only that the left moving and right moving oscillators were not independent. That was the point about the frequencies being set the same, despite using the cosines. Okay? So this zero mode part is not, but the zero mode part is also changing. So let's see. So now the zero mode part is changing because this integral goes from 0 to pi. So now in the open, now we'll redo this for open string. This will give us 1 by 4 alpha prime x dot square. Okay? So this part will become 2 alpha prime by 2 p square. Because if 2 alpha prime by 2, because half m square.
Okay,
Right? And then this will have to be equated with, with plus minus sign. Now just one of these factors. So n minus 1. Okay? So now p squared will be equal to 1 by alpha prime into n minus 1. So this factor of 4 is different. Okay? And this has its roots in the fact that there's only one zero mode, but yeah. So the interplay between the zero mode and the oscillator is a bit different in the open string and the closed string. But other than that, what you said is exactly right. Okay? Great. Notice the way we did this. Many of these factors in string theory are very easy to just work out yourself by hand rather than remembering a formula, as we just did. If you remember some basic things about the thing, and that's always safer to do than looking up somebody's conventions, because it may be a bit different from what you're doing. Okay, great. So let's proceed. Now, as we said, the key point for the open string was that you could replace a holomorphic part and an anti-holomorphic part in the upper half plane with a holomorphic function in the whole plane. Okay, what about operator insertions? Okay, so suppose I had some operator inserted like this. Okay, let this operator, for instance, be del zx. Okay, now how am I going to compute this operator insertion? Well, one way is, of course, to work in the upper half plane with our boundary conditions and insert this operator. But you see, what we really want to do is to make sure that this boundary condition is always maintained. Okay? And how are we going to ensure that the boundary condition is always maintained? Well, you can convince yourself the following is true.
A mirror.
Exactly. You use the image trick. That is, if you reflect this point down to its mirror image, and everywhere there's a z, replace it by z bar. You put this del z bar x. Oh, that was del z bar of the original x, but just del z of this extended x, because z bar is z in the extension. Okay? So you just put a mirror operator here.
This x tilde is not independent.
What? X tilde is not independent because it's just analytic continuation of x. That's another way of saying it. The fact that we got just a single analytic function on the whole space.
And it is unique.
What? Clear, because analytic continuation is unique. Okay? So that's another way of saying it. The fact that if we know the analytic part in the upper half plane,
We know the
we know the anti-analytic part, that is the same statement after this doubling as the statement that analytic continuation is unique. You have an analytic function up here, you can analytically continue down.
This full function only has analytic part, it doesn't have anti-analytic.
Exactly, it has only analytic parts. Okay? That's why here, if we're working with a full function, we can only do del zx. Del z bar is not even meaningful, which is 0. Okay? And you can convince yourself that doing this will preserve the boundary condition we want to do. It's basically an obvious statement. Okay? Similarly, if you had some insertion of tz, z here, you just reflect the insertion to tz, z here. Okay? So we've learned our second important thing. Is despite appearances, it's actually more difficult to compute closed string operator insertions in the open string. And now I have to say a few words about that, but by closed string operator insertions, what I mean, an operator in the bulk of the world sheet. That's not the only place you can insert an operator, because you also insert an operator at the boundary of the world sheet, and we're coming to that in a moment. But at the moment, let's look at closed string operator insertions. Here, this is more difficult to do because each insertion becomes effectively 2 insertions on the sphere. So if you want to compute some 4-point function of gravitons, you'll be computing some 8-point function on the sphere.
They will be sufficiently separated.
They will be integrated. I mean, some of them will be, you'll get to put them where you want, and some of them will be just integrated everywhere. There will be singularities when they approach each other also. That's what's on your mind. Will happen and has physical interpretation. But we come back. Yeah. Okay, but notice that if we were trying to compute purely open string scattering, then we never need vertex operators inserted in the bulk of the world sheet. Why is that? What is a vertex operator in the bulk of the world sheet? Well, we can take a little disk, do the conformal map, replace it by a tube that goes up to infinity, and have the wiggle. That's a closed sheet. Closed. We don't want that. What we want is a wiggle, a wiggly open string. How do we get that? By an insertion at the boundary. Because, as you remember, this strip, its wiggles, t equals minus infinity, approached 0, which is a point at the boundary. And then if you've got any insertion at the boundary, you can now make a little interval of that and do the transformation there. So that can be replaced by a strip going down all the way down to minus infinity. Just like a disk can map to a half cylinder, a finite strip can map to a half. Is this clear? So you see there are 2 kinds of strings world sheets we might want to look at scattering for. You might want to look at these cylinders coming in, or you might want to look at strips coming in. Strips coming in are open strings. Cylinders coming in are closed strings. Cylinders coming in can always be replaced by operators in the bulk. Strips coming in can always be replaced by operators on the boundary. Okay? And you might in the end be interested in computing scattering of open with closed strings. And that's fine. It just means you've got operator insertions on the bulk and on the boundary. Every operator insertion in the bulk is doubled using the doubling trick. But boundary operator insertions are not doubled because they're the fixed point of the doubling. Actually, there's one complication, there's one subtlety with boundary operator insertions. And the one subtlety with boundary operator insertions is that boundary operators have to be normal ordered differently from bulk operators. Why is that? Look, suppose you've got a bulk operator here, and so you're trying to define del x, the whole thing square, suppose, or e to the pi x, the whole thing square. So what you do is you take one operator here, another operator here, and bring it together. And then there's a singularity. You have to get rid of the singularity. That's the normal order. But remember, because we've got this boundary condition, you're also doing the same thing here. So you do this here, you do this there. That's the normal definition. But now you start bringing these to the bulk. You suddenly see that there are more singularities. Because now you've got this, and they're all together as you bring them to the boundary. So the additional singularities when you, okay? So the normal ordering that you need to do is also subtract things between images. Okay? And so when you define an operator inserted exactly at the boundary, that has to be normal ordered differently from an operator inserted anywhere in the bulk. There's an extra factor of 2 somewhere. Okay? And we will encounter this when we do our calculations. Okay? But once you keep that in mind, everything is very simple. You just have to do all the rules for string perturbation theory are just one half of the rules for the closed string with a few additional subtleties associated with boundary operators. Okay. The last thing is the following. The last thing is the following. You see, when we are interested in, when we were interested in the sphere, when we were looking at the sphere, we had C ghost insertions, no B ghost insertions. Something similar will be true. Now, the upper half plane is sometimes called the disk because the upper half plane can be conformally mapped to a unit disk. So I will sometimes say disk, although in all calculations we'll always use upper half plane. Topologically, the space is a disk. Okay, it's like a sphere with one boundary eaten out, with one hole eaten out. That's a disk. Okay, now you remember that the rules for string perturbation theory. Involved for the bosonic string perturbation theory involved these integrals over C ghosts, and in this particular case, no B ghosts. Okay. Now, what will we do with the insertions over C ghosts? Well, let's remember what the C ghosts were due to. The C ghosts were due to unfixed diffeomorphisms, and let's remember precisely which unfixed diffeomorphisms they were. Okay. For the case of the sphere, we worked them out. We worked them out many times. The CKVs, right? So Vz is equal to A plus Bz plus Cz squared, infinitesimally they take this thing, and Vz bar is equal to A bar plus B bar Z plus C bar Z squared. You remember many times we worked out that these things actually regular at infinity when you use the transformation properties. Z goes to 1 by Z, that kind of thing. Okay, now we want to know what diffeomorphisms survive with the open string. Now the open string is just the upper half plane, and we want it to remain the upper half plane. So it has to be those of the diffeomorphisms here that map the upper half plane to the upper half plane. Okay? And that tells you that A is equal to A bar, B is equal to B bar, and C is equal to C bar. So that at the boundary, the vector field is purely in the x direction. Right? Because if on the boundary Vz is equal to, on the boundary Z is equal to Z bar, sorry, on the boundary Z is equal to Z bar, okay, and then if on the boundary Vz is equal to Vz bar, then the whole vector, which is Vz plus Vz bar, is real. It's purely in the x direction. But that's what we want, right? We want something that doesn't change the boundary. So it has to be purely in the x direction. So Vz has to be equal to Vz bar. Is this clear? Okay? Which, but that, because Z is equal to Z bar on the boundary, that means A is A bar, B is B bar, C is C bar. Okay? So this tells us that we can take this vector field and also double it. It's just one analytic V, which is A plus BZ plus CZ. The Z bar part is just that vector field down there. So it will come as no surprise to you that the C ghosts then are just a single C ghost rather than C and C bar. But other than that, follow all the rules of the closed string. Because it's just one copy of the diffeomorphism that you're dealing with rather than two. Okay? This is the unfixed diffeomorphisms are different, but they're just half. Okay? So the rules for string perturbation theory firstly go as follows. Three operators have to be, we have three unfixed diffeomorphisms. Okay? These three unfixed diffeomorphisms are that part of SL2 R that leaves the boundary of the upper half plane, that leaves the real axis fixed. Infinitesimally it's these things. But there's a finite version of that. That part of SL2, SL2R times SL2R, SL2Z, whatever, the whole thing, that leaves the upper half plane, the boundary of the upper half plane fixed, maps the upper half plane to itself. Okay? And so there are three real numbers in the diffeomorphisms. So what we are supposed to do is the following. We are supposed to use up those diffeomorphisms. We're supposed to have three C ghost insertions. Okay? And we use up those diffeomorphisms by, if we have them, the simplest way is by fixing the positions of three boundary vertex operators. Okay? And then just proceed as before. We'll come back to the question of what happens if we don't have enough boundary vertex operators. Okay? But now let's keep going. Now that we understand enough to start doing a calculation, let's first do some calculations, then come back to formalism. Because now this is not the formalism part of the course. We had enough of that, right? Okay, so great. So now we're ready to start doing some calculations associated with the open string. Any questions or comments before that? Because Vz, you see, this vector field Vz plus Vz bar, I mean the whole vector, so let's look at it this way. The whole vector field is Vz del z plus Vz bar del z bar. But this should generate motion in purely the x direction. So that means so that the y part cancels. Okay? So that it leaves the upper half plane fixed, the boundary fixed. Okay, excellent. More questions, comments?
So if I want to consider like unified scattering of open and closed strings.
Yes.
So the sphere without the vertex operator. So basically I can put both these closed string vertex operator anywhere I want.
Yes.
But there would be one unique line where I have to attach the open strings.
Say that again.
So strips have to be only attached at one
at the boundary.
And the points have to be attached
Exactly. Closed strings can be attached anywhere in the bulk of the world sheet.
Yeah.
Open strings have to be attached on the boundaries of the world sheet.
Oh, yeah.
That's basically what you said, right? Okay, operators that are put at the boundaries of the world sheet. Okay, So now let's immediately start doing some calculations. Okay. So let us first compute the scattering of 3 open string tachyons. Okay, so we've got 3 open string tachyons. So we have e to the pi k1x at z1, but really this is sigma 1 because it's open string, so it's purely on the real axis. E to the pi k2 x at sigma 2 and e to the pi k3 x at sigma 3. Right. This is the expectation value we want to compute. We also have to multiply this by C of sigma 1, C of sigma 2, C of sigma 3. Because there's one C ghost attached to each open string insertion. Completely uses up the diffeomorphism invariance. Okay.
Differently because they are
different conformities. Right, because they're product conformity. There's no cross. Okay. So now let's look at this. This we already know. This is just a restriction to the real axis of the C partition function because it's just one analytic function. I should have said that. This doubly trick also works for the BC ghost system. Okay, that if you continue C to the anti-analytic part of C,
yeah.
I should have said a little more about this. Sorry. Mummy, I'm teaching a class at the moment. I'll call you a little later. Okay, yeah. Okay, so I should have said this. You work it out as an exercise. Remember that what the boundary conditions of C are follow from the fact that it's an infinitesimal diffeomorphism. What was C? C was the bosonic analog of the diffeomorphisms. Therefore, Cz was equal to Cz bar at the boundary of the string. Okay. Similarly, figure out what the boundary conditions for B are. You'll find B is equal to B bar. Bzz is Bz bar Z bar. Okay. And because of this Z and this Z bar, you can do the doubling trick. That you just define a Cz that is this up and this down, and because of this, it all works. It's nice and smooth as well. So once again, the C ghost BC system is just doing a calculation in a single BC system. Okay, but on the upper half plane. All the time, it's all the same thing. Okay. So all we have to do for this guy is to do the calculation we're very familiar with in the open string. Sorry, the closed string, just one copy of the holomorphic. So it was Z1 minus Z2, Z1 minus Z3, Z2 minus Z3, and then restrict to Z equals sigma. So what is this? This is sigma 1 minus sigma 2, sigma 1 minus sigma 3, sigma 2 minus sigma 3. All good? Okay. Now, what remains is this guy. Once again, this is computed by Wick's theorem. Now, I told you that the normal ordering was different for boundary insertions rather than bulk insertions. How do we see that? Well, we see that in this very simple way. We have x sigma. We have, if you remember, xz prime is equal to alpha prime by 2 log of z minus z prime mod square. But if you take that at the boundary, this becomes equal to alpha prime no by 2 log of sigma minus sigma prime. Because z is equal to z prime, z and z bar are the same at the boundary. Okay, so the 2-point function here for the x's at the boundary just becomes this. Okay, this extra factor of 2 is also associated with the change in normal ordering, because what you have to do in normal ordering is subtract out 2-point functions. So subtracting out twice of that. Right, that's this with the image of the image on the other side as well. That's the extra factor of 2. Okay, so now if we just want to compute the correlation functions, it's sort of obvious. You just use Wick's theorem, but with this 2-point function. You ignore self-contractions, use Wick's theorem with this 2-point function. So what would we get? We get from here e to the power, now ik, so minus k1 dot k2, and then 2-point function of x, which is alpha prime log of sigma minus sigma prime. Sigma 1 minus sigma 2. And I've got the minus right? Was that with a plus or a minus? Does somebody remember? Just check. By the minus? I think so too. Are you sure? Shall I check? Minus? Okay. Let's go with that. Minus, then this becomes minus and this becomes plus. And so this is e to the pi k1 dot k2, or this is sigma 1 minus sigma 2 to the power alpha prime k1 dot k2. And then sigma 1 minus sigma 3 alpha prime k1 dot k3, and sigma 1 minus sigma 2 alpha prime k1 dot k2 dot k3. Clear? Okay. Now all that remains is figuring out what this k1 dot k2 is. K1 dot k2 is equal to k1 plus k2, the whole thing squared, minus k1 squared minus k2 squared divided by 2. Okay. But this is effectively just one factor. Let's say k1 squared by 2, because one of these cancels this, because they're all the same mass. What? Minus. And this k1 squared, because we in mostly plus convention, is minus of m squared. So that's m squared divided by 2, where m squared is the tachyon mass. But m square, we figured out right at the beginning of the class, was equal to minus 1 over alpha prime. And now you're telling me we have some problems. Minus 1 over alpha prime. How have I messed this up? Just a minute. Minus 1 over alpha prime. So m square we're getting is minus 2 over alpha prime. No, what am I saying? Sorry.
M square is minus 2.
No, k1, sorry. Yeah, so we have m squared divided by 2, which was equal to minus 2 over 1 over 2 alpha prime. There's something is not matching because this is cancelled. C costs. Give me a minute. What have I messed up? Just 1 second. he has y12 to the power 2 alpha prime k1 dot k2. How did I mess that up? I had how did I mess that up? Just one second. I hope I haven't made a bad mistake. Just one second. I messed up something badly. Just one minute. No. I'm sorry. I'm sorry. I said something badly wrong. My calculation of this was just badly wrong. It was not a simple mistake. It was a bad conceptual mistake. So let's rewind and do it again. How are we going to define these operator insertions? Let's do that more carefully. Okay. Let's do that more carefully. And even my prescription of the normal ordering, I said with this there'll be an extra factor of 2. Let me rewind the last, everything having to do with these operator insertions. Let me rewind that and say it again. I'm sorry about this. Okay. Suppose I want to define this operator on the boundary. What I'm going to do is take the limit that this operator comes from the bulk and goes down here. Okay. But what I have to keep track of, so let's do it very carefully. So I've got something at Z and something reflected here. Okay. Now, so suppose I've got Z1, so I've got Z1 here, I've got Z2, I've got Z2 here, and I've got Z3, I've got some Z3 here. Whatever, Z3 bar, Z1 bar, Z2 bar, Z3 bar. Okay. Now, what I'm going to do is to take all contractions except those that would become singular when you reach the so of course you don't take contraction of this guy with itself, but you also don't take the contraction of this guy with this guy.
Oh, you have to take contraction of every mirror operator.
So we have to take this guy with this guy and this guy with this guy. What? What? There's no 2-point function for? No. Now it's one whole holomorphic field. We're using the double link. You see, you can't think that way because the reason there was no 2-point function earlier was that there was no boundary. Now, if we worked entirely on the upper half plane, there would be a 2-point function between x and x bar, which is the same as the 2-point function between x and x, but its reflected point is the doubling. Okay? So let's do this carefully now. Okay. So what we've got is we've got e to the power I k z 1 times e to the power I k1 x of z1 I k1 x of z1 bar. Okay. E to the power I k2 x of z2 e to the power I k2 x of z2 bar. All these 6 insertions. E to the power I k3 x of z3 e to the power I k3 x of z3 bar. And we have to take this whole thing using Wick's theorem, but omitting all insertions that would go singular as you go to the real axis. Okay? So you're not going to allow yourself to contract z1 with z1 bar, or z2 with z2 bar, or z3 with z3 bar. Okay? So what kind of contractions will you allow? We could allow, for instance, this guy with this guy.
All the rest.
Except that.
Except itself.
Well, none of them can contract with their partners.
Yeah. So you can contract with 4 of them. X of z1 can.
Yeah. So we could one contraction is this, another contraction is this. What?
No, I mean, no, z1 can contract with all these 4 guys here, right?
With
Z2
anyone. This guy can contract with any one of these.
Yes.
This guy can contract with anyone.
Yeah.
Right. Right. I was just giving an example. I think for instance, this is one allowed contraction.
Yes.
Okay. Another allowed contraction would be this, and so on. Okay. So now let's see. Every contraction will have z1, this guy.
Yeah. So the square root is now understood because it will contract once with z2 and once with z2. I mean, essentially the same point on the real axis. So the square root that you are getting is now squared.
Exactly, exactly. And what we have to make sure is that the whole answer is effectively squared. So let's just make sure that that's clear. What is the danger? It's
yeah. So
Yeah.
we have to omit the self contractions.
Yeah.
I think there's probably only one way to achieve
Yeah,
that.
yeah. Let's try. So we've got z1, z2, z3, z1 bar, z2 bar, z3 bar. Okay, let's try to make a way of contracting
So that there's
that
no horizontal contraction.
so that there's no horizontal, exactly. So let's z1 contracts, let's say, with z2. Now z2 cannot contract with z1.
Yeah. It has only one way to contract. If we have chosen.
Because if it contracted with this, then this guy would have to contract with itself, which is not allowed.
Yeah. Yes. So it has to go like that.
If this guy does this, then this guy does this.
Yeah.
Okay? And so what do we get?
Yeah, and also there could be contractions with the between the verticals. Z1 can go to Z.
Yeah. There are
Yeah.
there are 2 terms like this with
Yeah,
cyclic,
exactly.
and then there is a vertical.
And then there are vertical. Yeah, exactly.
From column 1 to column 2, there can be 2 contractions, and also between the columns themselves there can be.
Only one.
Oh yeah.
Right.
No, 2
Each
because
column
they
can have
yes,
one, and
there.
it has to be crossed.
Yeah, pairwise.
Just one minute. What we should be interested in is the effective 2-point function, right? Just one. Oh, this is confusing. I know how we got wrong. Yeah. You see, the best way to think of this is the following. Because we're never going to contract this guy with this guy.
Yeah.
Effectively, these are e to the power 2ik k1 x of z1.
Yes.
Okay?
Yeah.
Because we're never going to do that, it's effectively e to the power 2ik x of z1, e to the power 2ik k2 x of z2, and e to the power 2ik3 x of z3. And now we just use the holomorphic part of all. Now this is completely holomorphic calculation. We just use the holomorphic results. So now in a previous case we got k1 dot k2, well, there's an extra factor of 4 because each k is doubled. But in the previous case we used this Green's function, that was very bad. We should just use alpha prime by 2 but with the z's, because now we've got only a holomorphic x. Okay, so it's multiplying by 4 divided by 2.
Yeah.
So it's multiplying by 2. That's the way to think of this. Sorry. So I'm going to say it again.
The 4 for m square is coming from that 4.
What? The 4 was what it was. So let's now let's do it again. We have x1 minus x2 to the power k1 dot k2 with a 2 and alpha prime.
Actually, can you repeat the first logic?
Why
Why is it becoming 2 this way?
is it becoming 2? You see, because if these were numbers, it would just be e to the power, numbers add in the exponent.
Yeah.
The only thing that's not number about it is the contractions. But we're not going to allow self-contractions between this guy and this guy.
Yeah.
So effectively it's a number. So just e to the power 2i. Right? So, this looked very complicated because of some 6-point function. But because we're only interested in it, see, remember we're only interested in the limit z1 goes to z1 bar.
Yeah.
So the insertion points are going to the same thing. And we're not allowing contractions. So they're becoming the same operator without contractions, just square. That's the 2. Right? So it's a 3-point function once again, but with double the momentum.
Yeah.
Okay?
Yeah.
Now, but having thought of it this way, we're looking at this as a purely holomorphic field.
Yeah.
So we should just use the holomorphic part of the 2-point function. Okay? So 2-point function should be alpha prime log of z1 minus z2 by 2. Okay? So we had, so let's do it now. E to the power I k1 2 k1x, e to the power of sigma 1, e to the power I 2 k2 x of sigma 2. Now we use the 2-point function. So that's minus because of i's. 4 k1 dot k2 into alpha prime by 2. So that becomes sigma 1 minus sigma 2 to the power alpha prime k1 dot k2 with a leftover 2. Okay? Yeah, so sorry about that. That's the right way to think.
So the prescription is very straightforward. I mean, almost with some.
Yes. So effectively double the momenta
Yeah.
and use only holomorphic 2-point function.
This probably some rotational confusion I have is that the original string coordinates were sigma and tau.
Yes?
When we come here, the horizontal line is the.
You don't like sigma?
So this sigma is the sigma 1, sigma 2, the complex plane coordinates.
Yes, it's just what I call for the coordinate.
Yeah.
X. You can call it X if you want.
It's not the original.
It's not the original sigma.
I get it.
Okay? And now this works because 2 k1 dot k2 was minus m squared, which is minus 1 by alpha prime. So this is minus 1. So that cancels the factors of, it's even been rubbed out. The factors of
Oh, see,
y1 minus y2, y. Okay? So this is just a number. Okay? So 3-point scattering of 3 tachyons was just a number. As before, it's going to be proportional to a determinant, namely the disk determinant. And as before, it will be proportional to 3 factors of G open, or whatever, G tachyon. Okay? These factors of G tachyon, which are the unknown normalization factors that come with the tachyon. As before, relative normalizations between different open string states will be fixed by state operator map. But there's one overall normalization that we don't know about. So there'll be G tachyon cube, G open tachyon cube, disk determinant times 1. But actually there's one factor that we've missed, and that's a factor of 2. And this is what I want to tell you about. Okay? So the answer would have been, ignoring all these factors which will come in later, you would have said that the answer was 1. Okay? Actually the answer is 2. Why is the answer 2? That's sort of interesting. You see, what we did was the following. We fixed these vertex operators to some positions, let's say sigma 1, sigma 2, sigma 3. For instance, 1, 0, infinity, doesn't matter. Some positions on the boundary using diffeomorphisms. But diffeomorphisms are always single valued by definition. Okay? So suppose you've got some coordinate on the boundary, and now I'm reducing the fact that in some good coordinate system, this upper half plane would actually be a disk. So suppose I've got some good coordinate on the boundary, and the coordinate is running here. If I do a diffeomorphism, it is a single value, and restrict the diffeomorphism to the boundary. That is a single valued function on the boundary. Sigma prime is some single valued, some increasing function of, let's say sigma prime is some increasing function of sigma, never decreases, otherwise it becomes double valued. So now suppose I had my coordinates such that the first guy was here, the second guy was here, and the third guy was here. The diffeomorphisms tell us we can put them anywhere we want without changing the order. But the strips could have arranged themselves not in this order, but in the other order. There are only 2 cyclically inequivalent orders. There's this, or there's 1, 3, 2. Remember, it's a disk. It's just a question of, as you go around, let's say, clockwise, what order do you see them? Start with 1, then you get 3, 2, or you get 2, 3. These 2 cyclic orders cannot be reached from each other by diffeomorphisms. These are separate configurations. So when we mod out by diffeomorphisms, we have 1 for this and 1 for this. And so the actual answer is 2 rather than 1. Okay? Now this 2 looks a little silly, but it will soon become a more important factor, as you will see. Okay? Now, any questions or comments about this? These 3 are identical tachyons. But one of them carries momentum k1, the other carries momentum k2, the other carries momentum k3. So the guy with k1 could attach itself this way compared to the guy with k2 and the guy with k3, or the other way. So even though they're identical inherently, the momentum distinguishes them. So these are different configurations. Right? Think in terms of vertex operators. It's exact world sheet picture. If you're just computing correlation functions, you're just computing correlation functions. But you have to know where to insert the correlation functions.
I mean, this issue would not arise in on the sphere because it's
because you can always everything exactly. It's because the boundary is a line. The diffeomorphisms can't change order on a line. Okay. In terms of world sheet, just about correlation functions, it's just correlation functions. You insert them wherever you want. So this is not something that is a conformal field theory question. It's a question about string theory.
So for n open string insertions, there will be something like n minus 1 factorial.
Exactly.
Factor of that open string ambiguity.
Exactly right. You fix one of them because, and then the relative ordering is n minus 1 factorial. Okay, it's really a question of a given what are the diffeomorphism inequivalent classes of 3 points on a disk. It's that question. It's not a conformal field theory question. Okay? Excellent. So now we understand this tachyon. I'll take 10 minutes extra if you don't mind. Okay. Now I'm going to do something more. Everything with this open string so far was a little boring. And now we're going to encounter our first phenomenon that is purely open string. That is, that has no closed string counterpart. Janpin. And that is this. What we're going to do is to try to make a slightly more exciting open string than the one that we have looked at so far. And the slightly more exciting open string we're going to try to invent in the following way. So far we imagined that the open string was just an open string. Now suppose there are some boundary degrees of freedom living on the boundary of the open string. Okay? So it's a little more than just cutting the closed string. Or if you cut the closed string, in this case you find that there are some boundary degrees of freedom. Now the boundary degrees of freedom we're going to take are going to be very, so as not to mess up anything. We'll take very boring boundary degrees of freedom. Okay, so we're going to imagine that there is a Hilbert space, some n-dimensional Hilbert space that lives on each boundary. And the Hamiltonian for this n-dimensional Hilbert space is just 0. Okay, so the degrees of freedom, whatever they are, they just do not evolve along the boundary. If I tell you what my vector was in this n-dimensional Hilbert space, I will just stay there. And we're choosing such boring dynamics because anything that interacts runs into trouble. And we need to do more careful analysis about this. But you get, there's a boundary analog of the central charge. And that also has to do something nice for string theory to be well defined. It runs in, if you do anything more interesting, at least many simple, more interesting things, you run into trouble. So at the moment we're going to do something very boring, so boring that we can't run into trouble. Okay? And that boring thing is we'll just have this Hilbert space, just decoupled. It doesn't care what this string is doing, it's doing whatever it wants. This Hilbert space lives on the boundary and, coasts along. You're in a state, you stay in that state. Excellent. Now, so there is a basis of the state, basis is I runs from 1 to n, some basis, or some orthonormal basis, you don't care what it is. It's a very abstract Hilbert space, it's the space of, we'll soon see index structures for un. Okay, some very boring thing. Now, but it's important that it's local, so it's there at every boundary. So it's here, it's also here. Now if we want to specify a state, we have to specify what the oscillators are doing, but we also have to specify what's happening here and what's happening here. So the state is specified by specifying some matrix, we call it lambda ij, so that the state on the boundary is lambda I, ij, inj. Is this clear? Lambda is just any matrix. So apart from specifying what the oscillators are doing and what the zero mode is doing, I have to specify this matrix lambda ij. Given the matrix, it tells me which state in this funny Hilbert space I've got. Now, you see, now if you've got some string like this coming along like that, we've got 3 strings scattering like this. Okay? This goes to, what are the indices doing? If you had an I here, it would continue to an I here, because along boundaries it doesn't change. If you've got some index here, it continues here and so on. So indices are conserved along these lines. But the state itself has some lambda 1 ij, lambda 2 ij, lambda 3 ij. And therefore, if you do scattering in the tachyon, let's say for the 3 tachyon scattering, so now suppose we are in this upgraded open string theory, where you don't just have these boundaries, but you have these Hilbert space living on the edges of the boundaries. And you do 3 tachyon scattering. What will you get? What we will get is trace of lambda 1, lambda 2, lambda 3 plus trace of lambda 1, lambda 3, lambda 2 corresponding to the 2 different cyclical orderings. This is the grown-up version of 2. The thing when lambda was trivial was just 2, these 2 different cyclical orderings, become this structure. Okay? Lambdas, remember, are n cross n matrices, and we will soon identify them with generator matrices of un. Okay? These degrees of freedom that live on the world sheet of the string are called Chant-Paton factors. Okay? And this quantity here is the, okay, so now the scattering amplitude even for the open string tachyon is a little more interesting than for the closed string tachyon, because it's a trivial function of momenta, but a non-trivial function of these 3 matrices, the index matrices. Is this clear?
Sir, I don't understand this picture.
Good.
How these are connected. I mean, this is open string,
This is open string.
and then this is like a strip.
Yes.
And then
Now,
what it is.
you see, what we've got is a state here, which tells you that the state here, if you've got an I, you've got a J connected with a lambda. So this state allows you to change Chant-Paton factors. Right? It tells you how you're connecting one with this. For instance, you could have a 1 with here, with 2 with here. Along time evolution, that factor doesn't change. So whatever the factor was at the beginning here, it will be the same as the factor end here, and so on. But that's exactly what it traces. End index of one is beginning index of the other. End index of one is beginning index of the other. I've just drawn a pictorial representation, in fact, of the trace.
I
Is-
don't understand how this, I mean, previously you said the strip should be connected to the boundary.
This is the strip connected to the boundary.
Oh, this is the disk is the boundary.
I'm sorry, this is the, yes.
Now,
Now this is this.
now
I drew it that way to give you the logic.
and this is totally different from the previous one, like sphere or.
Yes, there's no analog of this on this. For instance, you see matrices, to multiply 3 matrices, you need an order. No possibility of an order on a sphere. But there's a possibility of an order on the boundary of a sphere, of a disk.
In the computation, where will the trace come from?
Where will the trace come from? It's right, exactly. What you're going to have to do is to do the partition function over the whole theory, including the boundary degrees of freedom. So the partition function here is just all states running, but nothing happens. Okay? So because you've got these insertions, you get this trace. If you had, right, exactly, because you have particular insertions, you get that trace. If you just had identity, it would, whatever that meant, that would not be good for scattering. But if you just had identity, you would basically get a factor of n. If all lambdas were identity, you would get trace of identity times identity times identity, therefore n. That would just be this disk with the partition function of the ordinary disk times the partition function over this boundary degree of freedom, but that's just n, because it carries no energy, and then there are n such copies, just the dimensionality of the Hilbert space. Yes, so 1 plus 1 became n, became this. Now, when was it 1 plus 1? it was 1 plus 1 when n was equal to 1. Suppose n was equal to 1, then we have a one-dimensional Hilbert space. That's absolute triviality. That was the calculation we did before. That would be, instead of n plus n, would be 1 plus 1. If you had an n-dimensional Hilbert space, it wouldn't have been 2. Even without these insertions, if there all be an identity, it would have been 2n. Okay? Excellent. So, we...
How are this boundary Hilbert space different than the Hilbert space created by the operator insertions?
Oh, it's very different, because you see, the operator insertions now would have to create a direct product Hilbert space. The Hilbert space of the oscillators plus the insertions of these boundary modes. It's just a direct product of something very trivial with what we had before.
Is it, maybe
Go on.
Here, but I'm saying, is it like working in some excited state rather than, I mean, I'm saying...
Not an oscillator excited state.
Not an oscillator excited, but some, I'm saying when I put insert, if I want to look at a sphere partition function with insertions, I can, or maybe if I want to look at scattering of some external states, I can look at sphere partition function with insertion of operators.
Yes.
Operators.
Yes.
So instead of that, now I have more insertion. The state is not sphere in the sense that there are some extra states that have been.
There is, in addition to the Hilbert space that you get by quantizing the motion and oscillators of the string, there is an additional sector of the Hilbert space. One sector which lives boundary by boundary.
Yeah.
Okay? If you did the state operator map, you would have to specify, states would specify not just an oscillator operator, but also lambda ij. An operator on this Hilbert space, which is a matrix. Okay? In general, actually, you could do more. You could have lambda 1 times one space state operator, some oscillator operator, plus lambda 1 2 times another oscillator. It doesn't have to be a direct product, it could be some of such terms.
Can I think of,
Go on.
is it related to some large difference of some degrees of freedom?
No. It's just put by hand. Just put by hand. It's perfectly consistent to work with n equals 1. In which case, there's none of this. Okay? As we go on with our studies, you will see what it really is. These things will be related to how many brains you have. You'll have a spacetime with brains. String theory in a spacetime with n brains is different from string theory in a spacetime with no brain, with one brain.
Yeah.
Okay? This is where it's going to come from. We'll have physical interpretation of it as we go on. But at the moment, on the level of the world shape, it is put by hand. You cannot understand it in terms of it had to be this, because there's a free parameter n, which is totally up to you. Okay, it's enhancement of the structures of string theory by hand. Okay? Now, you might wonder, does it all work? So far we were so careful about all these things. There will be some formal way of arguing, but really in the end, you try it and you check. It does all work. We've got 30 years of experience. Okay, then nothing goes wrong. We'll see some of this as we go along. And the key to it all working is that it was so trivial. Now there is a larger theory of this, which maybe at some point I will tell you about, called theory of boundary states. It's a theory of what kind of boundary conditions you are allowed to put. Okay? There's a large theory about this. These boundary conditions have to maintain conformal invariance and various other conditions. Okay? So this is not the only thing you could have done. And in more complicated string theories, I often end up doing more complicated things. Okay? But it turns out to be the only thing that you can do preserving Lorentz invariance. So if you want to get a Lorentz invariant fully nice Lorentz invariant spacetime theory, we're not missing anything. Okay? Maybe by the middle of, if we continue this course, would you guys like me to continue through the semester?
Yeah.
Okay, then we can just finish. Yeah. So then if we continue this course, I will tell you more about these boundary states and so on. So there's a theory developed around what you can do. But at the moment we're taking something so trivial, it would have been surprising if anything works, that if this did work. Okay, yes?
So if we did not put the Hamiltonian as 0,
Yes.
But instead considered a completely decoupled Hamiltonian from the full string Hamiltonian just acting on this space, I imagine even the simplest non-trivial Hamiltonian would be severely
Now,
constrained, or is
yeah.
H equals 0 only?
Yeah, you know, you're going to have trouble because you're going to have this Hamiltonian consistent with diffeomorphism invariance.
Right.
So you'll
that's
basically
what
be
I thought.
forced to be 0.
Yeah, I mean it has to be completely trivial.
Trivial, yeah.
Otherwise, there could be some crazy time-dependent states.
And time dependence in which time?
Yeah.
Because of diffeomorphism invariance.
Yeah.
Right, so it's very little you could have done without interacting with the x's. If you allow yourself to interact, there's sometimes more you get.
Huh. Yeah, but then it will be.
Then there's a whole
will
zoo
go
that
all over
opens
the
up.
place.
Yes. So we're not getting into that. And in this simple case, preserving Lorentz invariance, we don't miss anything. When you do more complicated theories, string theories for which the world sheet is Wess-Sumer or Witten theories, for instance, there are these interesting brains, interesting boundary conditions, which conformal field theory people love studying. Okay? And these are sometimes relevant for string theory. But later. All this later. Right now, just let's look at the simple case.
So for n greater than 3, depending on different ordering, n greater than 1, depending on different ordering of the operators, but the 3-point function is different.
Exactly. The 3-point function is different, and you have to sum over both
I see. Okay. With that particular factor.
with this factor to get the right answer.
I mean, the trace will weight each of the amplitudes, right?
The answer is trace plus trace, and these two traces are not the same. I think that's what he was saying. It's not that you can say it's either this or this.
Yeah.
It's not. It's this plus that.
The convention is always sum, but when n is 1, these factors are trivial.
Exactly, and therefore it's 1 plus 1, so it's 2. Okay? Now, I wanted to very quickly tell you about photons. Then we have to move to the superstring. So we have some way to go, but let's. You see, the analog, now in the open string, do you remember the mass square formula? Just like for the closed string, n equals 1 is special.
Mass square should be with
Plus,
minus.
plus, thank you. N equals 1 is special because it gives you a massless mode. Now, on the other hand, the massless mode is not a graviton because it comes with only one index. Okay? The vertex operator is del x mu. In the double trick, it's purely holomorphic. Okay? So now what we've got is, some del x mu. This is the vertex operator. This, the gauge invariance is del x mu, epsilon mu del x mu is identified with epsilon mu plus k mu del x mu, and of course epsilon dot k was 0. Okay, and very plausibly, this massless mode with this gauge invariance is going to represent a gauge boson rather than graviton. But now we've got something interesting going on here, because we've got gauge bosons and we've got these matrices. So we could plausibly recover non-abelian. Non-abelian invariance. That's what we're going to do. By the way, this scattering amplitude here, can you tell me what local Lagrangian would reproduce it?
Which
This sum over lambda 1
yeah,
trace.
I mean, just some phi a scale. I mean, some a tachyonic scalar with some global symmetry, some UN, some fundamental of UN.
Adjoint of UN.
Okay.
Trace T cube.
Okay.
Suppose T was in the adjoint of UN. And we consider the Lagrangian trace T cube.
Yeah, at two indices.
Two indices.
Yeah.
Exactly. Now we consider the scattering matrix of something with polarization lambda 1, lambda 2, lambda 3. Okay? Now you see our vertex is this. That's the trace T cube. And I have to attach something here, something here, something here. But I can attach K1, K2, K3 in any order. And therefore, I will get both these cyclic structures, right? So just trace T cube, where trace is over UN indices, is the local Lagrangian that reproduces the structure. The cyclic orderings is just the fact that a single Lagrangian has to be connected in every way, and that gives you the various cyclic orders. Okay, let us very quickly now start discussing gauge bosons. Let's not do 3 gauge bosons today. What we'll do is 1 gauge boson and 2 tachyons. Okay. So we have e to the pi k x of sigma 1, k dot x, e to the pi k dot x of sigma 2, e to the pi k dot x of sigma 3. But let's say that sigma 1, for instance, also contains del x mu epsilon mu.
So because of doubling, each of the exponent will be multiplied by 2 eventually, right?
Eventually will be multiplied by 2, exactly. So let's just put that here. I mean, the physical momentum is k, but the effective vertex operator is this object here. Okay, maybe let me just leave this as an exercise for you guys, okay, and which we'll do in class next time. Okay, it's got late. Let's leave this as an exercise for you guys. Compute this.
This epsilon mu del x mu will not be squared.
Epsilon mu del x mu will not be squared. Well, the principle is always we double. No, it will not be squared. But you see, we have one insertion here and one insertion here. Okay, but it's not squaring because
There could be some overall factor.
exactly. So what's going to happen here is yeah, let's think about that. I think that effectively there will be an extra factor of 2. You see, let's remember what this 2-point function, that 2-point function was. Let's just work it out. Okay, we had a del x here, and e to the pi k1 dot x, e to the pi k2 dot x. Now you remember we had this formula for del e to the pi k's inserted. Okay, and that formula did the following thing. It said either you what?
There is also k1.
Both are k1. Right. And then here e to the pi k2 dot x, 2k2 dot x e to the pi 2k3 dot x. Now this formula said the following. It said either these two contract with each other or these contract with objects. If they contract with objects, we just replaced this k, this del x here, with some factor that was associated with these k's. We'll have to do that replacement here as well as here. So there will be some sort of effective doubling. Why don't you work that out, and we'll do it in class carefully next slide. But do work out this exercise. Okay, this is one thing to be careful about, exactly what Shubhan said, to get all the factors right. I messed, the analog of the factors I messed up for the tachyon, get them right for this guy. Okay, the second thing that we want to do is to be very careful about the orderings. Okay, there will be
now two identical and one
there will still be two orderings.
Yes.
Okay, there will still be two orderings, but you have to be very careful about relative signs of the contributions of the two orderings. Let me warn you about that. Why do I know that you have to be? What do you expect the answer here to be? Anyone has a guess? What? I didn't understand. The structure for the amplitude? Good. So epsilon dot k2 minus 3, k2 minus k3. That's the only, you're right, this thing here. But now this thing here looks like it is asymmetric between 2 and 3. So this is going to multiply trace of lambda 1 commutator lambda 2. Because now that makes it symmetric. And getting the sign, the minus sign for this commutator, right, requires care. So look at it carefully, try to work this out. Okay? This is what you should have expected, because the Lagrangian is going to be d mu t, d mu t. It's an adjoint tachyon. Okay? So the d mu has a term which is a mu commutator t. So the effective term will come from here, trace, and that's going to produce this structure. Okay, one of them is still d mu. That d mu will produce your this quantity, and this part will produce this part. Okay, so from 2 points of view, we expect the same thing, and we will get the same thing if you're careful about signs. So why don't you guys try this, and on Friday we'll look at it carefully.
This means that immediately implies that the photon tachyon scattering amplitude vanishes.
A photon tachyon has scattering amplitude vanishes. Now why must that be? Any suggestions?
Oh, because photon can only couple to charged scalar.
Excellent.
Tachyons are uncharged.
Excellent. Adjoint, you see the tachyons are the adjoint. Adjoint for U1 is uncharged. The uncharged scalars are not charged under photons, so do not produce them. You can have a coupling between something uncharged and f square. You could have something like phi square f square, but that doesn't show up in a 3-point function. The coupling between a gauge boson and anything else is a measure of charge. So this is the current of the tachyon, which is 0, as you said, because for U1 the tachyon is uncharged. So you should have expected that scalar photon would just be 0 if the scalar is uncharged. Exactly, and here of course we see that, because if it's a 1×1 matrix, then any commutator vanishes. Okay, we'll continue our discussion of open strings next time.